This is what your test is your quiz is gonna be on next class. Conceptual problems like vocabulary. Even question number 2 is conceptual. And then a simple calculation because our wave equations are pretty simple. So what I want to go over is the definitions. Let me grab my warm-up. Okay, first one is a transverse wave. I have an image with a slinky. It has peaks. It has crests and troughs. I need to use the right vocabulary. And then the definition is that it moves at right angles or perpendicular to the medium. Another good vocabulary word. The medium is the substance in which your wave is traveling through, which is the slinky itself. So the coils or the particles in your medium will travel perpendicular or at right angles to the motion of the wave. Now, a longitudinal wave has parallel motion, meaning the particles are going to move parallel to the energy of the wave or the motion or speed of the wave. And we've got, it looks a little bit more like this. No ups and downs, but just compressions and then spread out portions, refractions, which is our other vocabulary. Wavelength is not equal to the period, but the period is the amount of time for one wavelength to pass. You want one full cycle, means one cycle before it repeats. So you can take trough to trough or crest to crest. You could also take equilibrium up, down, and back to equilibrium. It depends on what the wave looks like. So you want to make sure you know all different methods of finding wavelength. Here, the amplitude, it says the max height of the wave between the middle and the crest. The middle is your equilibrium. So you want to know that vocabulary. Equilibrium is the middle and to the top, not top to bottom. It's also equilibrium down to a trough, which should be the same amount as equilibrium up to crest. If you do top to bottom, divide it by 2, because it's half of that. Any questions on amplitude? All right, so period is the time it takes for one cycle. In your worksheet, it's going to give you a bunch of period values. The problem is they're not just going to do one cycle, they're going to do multiple cycles. So I'll talk about that in a little bit. And it's represented by a capital T. Some students want to make it a capital P, but it's capital T for period in seconds. Now, a compression, this isn't a very clear compression, so I'm going to draw more spaced out coils. A compression is kind of self-explanatory, right? It's where your coils are close together. So here's my close together coils, here's my far apart coils. And the rarefaction is the opposite, meaning it's more spaced out in your longitudinal wave. So the part of a longitudinal wave that is not compressed. Any questions on this vocabulary? Okay, let's do some problem solving. So we had a lab, we had a lab that had us test different characteristics of a wave to see which one moved faster. If the medium is solid, in other words, solid, gas, or liquid. Okay, so this is talking about sound waves. Solid, gas, or liquid. This is talking about sound waves. And sound waves are very specific to this characteristic. Sound waves are going to travel fast through gas, and it's going to slowest through gas, so through air, and fastest through a solid. And we're going to talk about this a little bit later. But if we weren't talking about sound waves, not sound, so let's talk about slinkies because that's what we did in our slinky lab. What characteristics in our slinky lab made it move faster? Mason?
Less density.
Density, less dense, and that's because of inertia. If you have more mass, it's going to be harder to move. So less dense moves faster. What else? Queen? More tension. And that's because of the restorative force. A restorative force is going to have more force bringing it back to equilibrium. So that's what allows it to move faster. There was one more. What am I looking for? What else makes a wave move fast? Any thoughts? Alec?
What was it? Like the wavelength and frequency?
So we're going to talk about wavelength and frequency when we do the post lab. So the speed equation is wavelength and frequency. Unfortunately, it seems like the frequency and wavelength affect the velocity, but the velocity is set. The frequency affects the wavelength, and the wavelength affects the frequency. So these variables, even though they make the equation for wave speed, they do not affect wave speed. So anyone have an idea what the third thing is that affects wave speed from our Slinky lab? Type of wave. So this is the wave type, and it is the longitudinal. Longitudinal. The reason why is because there's less displacement. Your wave particles are moving in the same direction as your wave speed. It makes it easier for the wave to travel. Same direction of particles to wave speed. So not as much displacement when you have a longitudinal wave. Makes it move faster. So the last part is a problem-solving problem. This one had two types of calculations to it. So what Vincent did here is he took his velocity, 13 meters per second. I always like to write the guess method. He took his his 7 meters, and he put that in as his wavelength. And then he used his equation that velocity is equal to wavelength times frequency. The problem is, so he did this calculation, frequency is not what we're solving for. We're solving for period. So if he calculates his frequency to be 1.857, he has to take the reciprocal of that to get an actual time. Now, his time here is 0.539 seconds. Is that your final answer? What do we have to do? What else do we have to do to get our final answer for this one? It says calculate the time it took for the wave pulse to travel away and back to you. This is the distance it traveled away, right? So what do I have to do? Double it. Just multiply it by 2 because the time it takes to go there is going to be the time it takes to come back. This is going to be 1.08 seconds. 1.08 seconds if you double the time.
Why wouldn't you just say that 7 meters there and back, so 14 meters, and just divide that by this?
So there's another way to do it. And all you have to do to get your time straight off the bat without having to do 2 steps is use the velocity equation that we used in kinematics. Velocity is distance over time. We have a velocity. Instead of wavelength, our lambda is equal to distance. And so if I did this calculation, 13 is equal to 7 meters over time. My time would equal 7 over 13, which is equal to 0.539. Of course, you have to double it, and you still get the same answer. So either method gets you the same answer. This is the method I would have done as well.